me show you how to be a good breezy and change your predictions after.
Ben Vincent, welcome to Learning Bayesian Statistics.
Hi Alex, it's very good to be here.
Yeah, I'm really happy to have you on the show because we've been working together for quite a while now, and I wanted to have you on the show for a while, but wanted to find the right angle because you do so many things that like I don't know which one we should focus on. So fortunately, I made my choice, and today we're mainly gonna talk about causal inference, but of course, you do a lot of things, so we'll see where the discussion takes us. Also, I shared that recording link in the Slack channel of the patrons of the show, so maybe some of them will show up at some point in the audience and we'll have some live question. Maybe it will just be the two of us. We'll see what life has for us. Yeah, basically that's it from my end. A quick note that I am, as you may hear, a bit sick, so I'm gonna try to cough as little as possible, but I cannot make, that's the only promise I can make. Okay, so let's dive in, and as usual, let's start with your origin story, Ben. So how did you come to the fabulous world of statistics and probabilistic modeling, and how sinuous of a path was it?
Yeah, so it certainly wasn't direct. So I think most people I know have some kind of formal education in stats training to some capacity, whereas I didn't really have any. So for many years I was teaching, I was faculty in an experimental psychology department. And of course there we start the undergraduates off quite early with stats. Of course it's all frequentist. But I didn't have any of that. My undergrad and PhD was basically neuroscience. And well, clearly it's a quantitative topic. You didn't really get the same immersion in statistical training that you would in experimental psychology, for example. So I was definitely a latecomer. That said, I think my PhD and postdoc prepared me well on the kind of quantitative way of thinking, particularly programming and things like that. So my background with coding started at a very young age, and I think that so started off probably when I was about 7.
Oh damn.
And so I learned BBC Basic very early on, and I think that was
BBC Basic. Is that related to the BBC, the British Broadcast Channel, in any way or not?
It is, yeah, it is. So I'm not 100% sure exactly how that came about, but in the kind of relatively early days of computing, I think that there was this kind of clear prediction that people made that computing was going to be a big thing. And so the BBC, as kind of in its kind of educational capacity, started to kind of get involved in this, and they maybe supported the development of a language for I think it was like BBC microsystems or Acorn microsystems. I can't quite remember. I was only 7. So yeah, that was a very kind of early introduction into coding, and I think people who code obviously kind of appreciate that it makes you think slightly differently. So it gives you a good foundation, I think. Anyway, so my PhD kind of involved modeling neural networks, And so the basic idea was to answer a question really about the human brain, about physiology. So the question is, how does the brain actually wire itself up? Are there any underlying principles that we can use in order to kind of understand this very complicated organ? And my particular PhD basically was looking at the question of the role of energy efficiency in neural networks. And
Okay.
we basically used the visual system because as like a model system, because the neural wiring of the visual system is really well known. So what that allowed us to do was to make these little neural network simulations and put in various different costs, like for example, it's similar to what we now know as weight decay in machine learning, or you could even think of it as like Laplacian priors from the Bayesian perspective. But from a physiology perspective, you can basically think of these things as energetic costs. So for every connection between one neuron and another, you can imagine that that takes energy in order to transmit information through the synapses. And you also have costs simply for the number of neurons that you have. So we were trying to understand why we have this quite peculiar arrangement of the visual system. So anyway, we were doing coding, very early neural network stuff. Compared to the things that people do now, it was trivial. So this was back in the era of shallow neural networks, and also there wasn't any Bayesian stuff in sight at this point. So later on, I kind of started to get more exposed to, well, in fact, during my PhD, I was kind of exposed to the Bayesian way of thinking through my supervisor. That's Dr. Roland Badley. And the way how he presented it was sufficiently like simple in terms of the conceptual basis of Bayesian inference is seductively simple. And so you kind of think that you get it straight away.
Yeah.
But then when you try to actually think about it in concrete terms and maybe implement something without a whole bunch of additional stuff, it actually starts to get quite tricky. So I spent a long period where I was kind of convinced that the Bayesian approach was definitely interesting and it sounded sufficiently contrarian for me to be interested. But it wasn't maybe until the postdoc phase and early in my lectureship that I felt like I really had like a decent understanding to the extent that I could code these things up myself.
Yeah, that's super cool. I didn't know you started so so early, actually, in your BBC time, and I do agree that it's really cool to start so early. Not really for the language barrier, but I would say, as you were saying, for the kind of skills that it gives you, in the sense that it teaches you how to basically fail all the time and be okay with failure and iterative improvement, and in a way not only looking for success but also being comfortable failing in a way, which is something that at least in my education in France lacked a lot. I don't know about now, but it's like really trying to make you say the things that you have to say to have a good grade instead of making you think through a solution. So really rewarding the result much more than the path to get to the result.
Yeah, completely. I think the way how the particular thinking skills it gives you I think are fantastic. And I didn't think about it back then, but the way how I might think about it now is I was doing, silly stuff. Like I was simulating what happens if you have like little bacteria, which are just represented by pixels on your screen. And they kind of move around and there's food. And every time they get enough food, then they replicate. But if they don't get enough food, then they die. So you're basically creating your own miniature simplified world where you have clear, well-defined rules. And I might call that now like a data generating process, because you can tweak, what's the lifespan, how much food do they need, and different kind of outcomes happen. So I really wish at some point, even at that point, I think my brain would have been amenable to Bayesian thinking, because there you're basically just doing the opposite of that.
Yeah. Talking about Bayesian thinking, do you remember when you were first introduced to Bayesian methods and why they stuck with you?
Yeah, so I think broadly speaking, the core kind of introduction to the Bayesian ideas was through my supervisor, Roland Badley. But because the Bayesian ideas didn't directly relate to the PhD work that I was doing, the actual concrete implementation of it was maybe left a little bit opaque at that point. So I think really the exact point is kind of hard to define, but during my postdoc and early faculty time, I started to kind of shift just from making models which you kind of qualitatively compare to something that you might know and see if it's a good fit, to now try to quantitatively compare these models that you create to what we know about how people behave. So in particular, coming at it from like a cognitive experimental psychology perspective, we were trying to model visual attention. So both overt visual attention, which is basically how do I move my eyes around in order to gather information that I might need in order to solve problems and complete tasks. But then you also have this thing called covert visual attention, which is maybe what most people kind of think of when that phrase is mentioned, is basically if you have a whole bunch of information coming in, some of that stuff is going to be more relevant to you than other stuff. And so if you can narrow your attention on the kind of appropriate information, then you're essentially increasing your signal to noise ratio. You're gathering in the information that is informative to help make a decision and kind of eliminating some of the information that is not relevant. And so we tried to set up experiments both with eye movements and covert attention, where we basically put real people in psychology experiments. We made them look at computer screens and we showed them different kind of simplified visual situations, and we gave them certain tasks. And kind of our approach as modelers was to basically think up of possible ways, like what's going on inside this black box brain that is actually leading them to behave in a certain way, solve a problem in a certain way. So the core of that, the kind of Bayesian way of thinking that Roland introduced to me was basically translated into that. So we were essentially asking, how would we expect people to behave, or how would we expect them to solve a problem if they were Bayesian? So stepping back a little bit, I kind of see it almost as jumping into the kind of slightly more complex side of Bayes before the kind of easier side. So the easier side, I guess, or the main way how Bayes is kind of brought up to people is through like describing your data. So what we might call like regular statistics. But Bayesian modeling is a little bit slightly different in that you're not just trying to describe the data as such, but you're more actually trying to really describe the data generating process. And that, in this case, involved like human cognition.
Yeah, I see. Yeah, super interesting. And so that's how basically you started doing Bayes, and now you are basically doing that full time, right? So yeah, maybe define the work that you're doing nowadays for listeners, and also the topics that you are particularly interested in.
Yeah, sure. So the main stuff that I'm doing at the moment is basically working as a consultant data scientist, and most of that stuff is through PyMC Labs, and that's largely how we know each other. I do a little bit of random consulting on the side, but the majority of it is through PyMC Labs. So we do a bunch of different things. So part of it is educational. So I think after all my years of teaching in academia, that maybe set me up to enjoy teaching Bayesian methods to people in industry. But we also just develop novel models and solve hard problems for people who have kind of challenging data science questions in order to solve business problems in industry. So that's the majority of what I'm doing.
That sounds like fun.
It is.
Yeah, and actually, you do a lot of causal inference. We'll get back to the teaching aspect if we have time at the end of the show, because that's always also something that I'm very interested in. But yeah, like to start diving in a bit about your main focus these days, let's talk about causal inference. So can you define causal inference for us and tell us how it differs, if it differs, from Bayesian stats?
Yeah, so just to kind of put this in context, I thought that over the years of exposure and kind of experience to Bayesian inference that I was a reasonably clued up scientist and now data scientist. But then I kind of became aware through a really bizarre kind of situation that I was actually completely clueless about causality. And I think that this is actually like a something that bubbles away in the brains of many academics, because in the same way that I didn't have formal training in statistics, I think that unless you're kind of lucky, maybe you're in an area of epidemiology, for example, I think it's extremely rare to get formal training in causal inference. And so a lot of the ideas that we gather over time about causality focus mostly on kind of heuristics and things like this, and not very much on kind of formal ideas about what causality is. Mm-hmm. So yeah, do you want me to go on and describe like what causality is, or expand a bit on how I got interested in causality?
Yeah, maybe define a bit the causality part, basically to set the ground up for people so that they understand the difference with Bayesian stats, and then we'll dig into CausalPy to actually do causal inference in the Bayesian framework.
Sure. So, I mean, one way how you can slice things up is to basically think of statistical relationships as being kind of one particular thing. And then you could further subdivide that into, are you going to take a frequentist approach or a Bayesian approach? And the other kind of angle would be looking at causal relationships, and you could almost think of that as orthogonal to what particular statistical approach you use, whether it's frequentist or Bayesian. But really, the way how I would kind of describe a causal relationship, I think this is going to be fairly close to the kosher definition, is that a relationship can be said to be causal if you go in and intervene on the cause, and that then changes the effect. And that opens up a whole bunch of questions like, how do you know whether this thing really causes something else? Because you can't simultaneously kind of fall off a bike and not fall off a bike. So, I think the key thing in my mind is if you intervene and that changes an outcome, then you can describe that relationship as causal.
Yeah.
Anything else is basically statistical. There's no directionality there.
I see. And so my kind of question would be, well then, why aren't we doing that all the time? And are there circumstances in which causal inference is most helpful?
Yeah, so in terms of why aren't we doing that all the time is an exceedingly good question, because the way, if you were to kind of list out the order of topics in a book, or in terms of how people might come across it or the level of perceived difficulty, then it might be something like linear modeling type of stuff, like t-tests, ANOVAs, and then you might learn kind of hierarchical stuff, and then you might learn, all of this stuff that I learn can be approached from the Bayesian perspective, and life actually gets much simpler if you're a Bayesian. And so you might ask kind of, why didn't they just teach me the Bayesian stuff to begin with? Mm-hmm. But then, you're looking toward the back of the book, the more complex chapters on causality, and you think, wow, this is like advanced stuff. But again, I'm kind of asking myself, why isn't this stuff taught as, why isn't there a module, for example, that all undergraduates take in year one on causal inference? Because this stuff can actually be taught without getting that quantitative, to be honest. Largely, the majority of it can just be taught with a set of ideas and words and just concepts without having to get into maths or coding. Mm-hmm. That certainly does add to your level of understanding. But yeah, I don't really know a good answer, but it's probably the same as why aren't we all learning Bayesian stuff first rather than frequentist stuff?
Yeah. I mean, do you think it could be due to the fact that, because, I mean, definitely one of the reasons that not everybody is using Bayesian stat is, well, sometimes it's not the right tool, but also, historically, it's been a bit harder to do. Now it's way easier, and so, with path dependency, things take always a bit of time to compensate, right?
Yeah.
So is there something related with causal inference? And it's actually a question I wanted to ask you, which are mainly, what are some of the challenges or limitations that practitioners face when doing causal inference currently? Because that could be also a factor that impedes the usefulness and the utility of causal inference tools.
Yeah, so I think So just stepping back slightly, I think that you're right. There is a historical kind of effect that probably explains why we don't all learn causal inference in primary school. I think going forward, that doesn't necessarily have to be the case, because now, just in the same way that we have really great kind of educational material for Bayesian inference, and we have really cool, kind of relatively easy to use probabilistic programming languages, that stuff can be bootstrapped, I guess, to teach you about causal inference. So I found, as I was kind of learning, and I'm still very much learning about causal inference, I found that a lot of those concepts were easier having a background in Bayesian inference, because you already know about the concepts of directed acyclic graphs, for example, and you already know about observing variables. And so there are only like a handful of key concepts that you need to learn on top of that before you can start really diving in and start simulating real things to get a sense that you really understand what's going on.
Yeah, I mean, to me, the Bayesian framework is really close already to the causal inference framework, because that generative modeling perspective is so ingrained in the Bayesian framework that once you're here already, well, that you already have a foot in the door in a way.
Yeah, I mean, the way of kind of describing models in terms of these directed acyclic graphs, where you have these kind of pointy arrows, and in Bayesian inference, that kind of implies causality, but it doesn't kind of necessitate it as such. But yeah, once you know some of those concepts, then it's not a whole bunch more you need to learn on top of that before you can really feel like you're getting somewhere. But I think I missed out one of your questions earlier of like, under what circumstances can causal inference be most helpful? So right. I missed that before.
I mean, I think I interrupted you, so it's all on me.
So
yeah, go ahead.
Yeah.
Good point.
So to answer my own question then, I mean, I think that there are a whole bunch of situations where it can be incredibly useful. So the first one is where there are a bunch of things called statistical paradoxes. And we all know that kind of paradoxes typically are just not really paradoxes, but just expose not really the correct understanding of how things work. So you can come across certain results, certain kind of empirical results and relationships between variables that really make you scratch your head and confuse you if you're coming from purely a statistical point of view. But once you start adding on a layer of causal thinking on top of that, all of a sudden there are kind of very intuitive and appealing explanations for these things that previously were quite confusing. So I guess that's like an intellectual and practical thing. There's just moving from a situation where you don't really understand the data that you're looking at to getting a much better understanding. I think the other situation that I would say is really key when causal inference is most helpful is when you are doing kind of high stakes interventions. So if you take purely a statistical point of view, you could be trying to do something like predict house prices based on a whole bunch of different predictor variables. And let's say your data set comes entirely from a a low inflation era or low interest rate era, and you maybe you do have the interest rates in your model, but the way in which you've structured your model and your causal understanding is purely from like a statistical perspective and not necessarily from a causal perspective. And so if you go in and change things, like you start marketing in a different way, for example, or you move into a different regime where interest rates are much higher, you could come up with like embarrassingly wrong predictions when you take purely a statistical approach. Taking a causal approach definitely does not guarantee that you're always going to make fantastic predictions, but I think it would in general make you a little bit less wrong than if you took purely a statistical approach.
Yeah, in the kind of like in the long run, that should be the best bet.
Yeah, and when the stakes are very high, then that becomes increasingly important. So in medical situations, for example, if you are going to intervene in the form of like a surgery or a lifestyle intervention, you don't want to be doing that on some kind of downstream effect, that like treating a symptom, for example, rather than an underlying cause.
Yeah, for sure. And I mean, actually, I think we're pretty well set up now to talk a bit more in detail about CausalPy, which is one of the open source packages that you've single-handedly developed for all of us in the world. So yeah, can you give us an overview of CausalPy and tell us how it tries to solve these challenges?
Yeah, so I mean, just to say, I kind of led the coding efforts, but I did definitely have some input and help from people. So CausalPy is a Python-based package for doing causal inference. Now, just like how Bayes is a particularly large field of study, so is causal inference. And so we absolutely do not try to create one overall overarching package that deals with all causal problems. So we completely ignore a whole bunch of areas in the causal space. Like, one thing that we completely ignore is what's called causal discovery. So this is where you may be given a bunch of data, and your task might be to discover what the causal relationships are between the variables, kind of automatically. And that's something that is hard, and there are many packages already developed that try to do that with varying levels of success. Rather, so CausalPy focuses on a small domain called quasi-experiments. So quasi-experiments are also known as natural experiments, and they differ in one key way from real experiments, namely that we do not have randomization in how we assign people or countries or companies, whatever the unit of measurement is. We do not randomly assign them to different groups. And so there are many different situations where that can arise. So an example might be Brexit. So if you think of Brexit as an experimental intervention and think of, well, what are the downstream effects of that intervention? In an ideal world, what you might do is conduct a randomized control trial and randomly assign Brexit-type events to a bunch of different countries and see what happens. And the idea there is that you're taking away the influence of confounding variables. So in this Brexit example, you could think of each country has different compositions of social and political and economic thoughts, for example, and different economic conditions that the people are exposed to. Now, the problem, if you try to kind of ask the question of what's the causal impact of Brexit, is that if you look at the consequences, you don't know very convincingly whether those consequences are due to the actual treatment, the Brexit, or the kind of underlying confounding variables of the particular kind of socioeconomic situation at the time.
Yeah.
So there are all kinds of situations like this where you just can't run a randomized control trial. And so you're left with quasi-experiments, natural experiments, also known as kind of observational data sets. And all of these different situations can be subtly different, have different types of characteristics. And so there are a family of analysis methods that have evolved over time in order to basically help you analyze data in different types of situations. CausalPy tries to bring together into one package a whole set of these things, but present a kind of a unified API and try to kind of strip down the ideas to kind of core basics so that it becomes much more approachable for people who want to run these kinds of analyses.
Yeah. That's super interesting. And I mean, is there any real world applications of CausalPy that you'd like to highlight today?
Yeah. So aside from the kind of Brexit application, and that has actually been used, another kind of really cool real world one, which we're kind of seeing is particularly relevant in the kind of marketing domain, is this idea of geo-experiments. So the idea here is that if you launch, let's say, a marketing campaign, or you do store renovations, you can't randomly assign which individual people are then exposed to that, because presumably it's going to be, if you do store renovations in an entire country, then everybody who goes to that store is going to be exposed to it. Similarly, if you launch a new advertising campaign, you're not randomizing which individuals are exposed to that. The idea of geo-experiments are basically that you have different geographical areas, some of which are exposed to some treatment or intervention. And I mentioned the examples could be a marketing campaign or like store renovation, that kind of thing.
Yeah.
So the question you would have is, did the intervention that maybe cost me money to do, did that actually have a causal influence on an outcome that I'm interested in, like sales, for example? Or would those changes have happened regardless? And so that is tricky, because you don't necessarily have a random assignment of which geographical region was actually exposed to the treatment.
Yeah.
And you are likely to get systematic differences between each of the geographical regions. So it's quite likely that you'll have these kind of confounding variables that might influence the outcome, other than the treatment that you're interested in. So for that, CausalPy can help, because we have a synthetic control analysis method in there, which you can basically use. And this is one of the examples that we've actually put into the package. So many like real world applications of that.
Yeah, and we'll definitely put these links into the show notes. They are on the documentation for CausalPy, so for sure, folks, feel free to check this out. And I maybe something I wanna precise a bit is that idea of quasi-experiments. So maybe can you define that a bit more for listeners, because I think it's the first time we mentioned that on the show. So like what is a quasi-experiment and when would that be useful?
Yeah, so quasi-experiments would also known as natural experiments. So I think one of the key characteristics of, let's say, real experiments or randomized control trials would be the idea of a control group and a treatment group. And so you have your intervention, whatever it may be, like vitamin D supplementation, as compared to not having vitamin D supplementation. So if you can, then the best thing to do would be to randomize which people get vitamin D supplementation or which people don't. And the key reason for that is because people differ in very many different ways. And so by randomly allocating, rather than letting people decide for themselves if they want to have vitamin D, you're then essentially making the control group and the treatment group comparable. They will have similar characteristics. And so if you look at and find differences in some kind of health outcome between the groups, you can then attribute that purely down to whether someone was in the treatment versus the control group, because the groups are largely identical because of the randomization. Now, a very kind of obvious situation where you can't do that is with smoking, for example. So if you want to know what is the causal effect upon health of smoking, you can't come along and do a randomized control trial, because if you really do suspect that it has negative health impacts, then that would be not a very friendly thing to do. And there are some things where you just literally physically cannot randomly assign things. So you can't randomly assign people to be born in different countries, for example, unless you want to get involved in large-scale baby abduction, which I'm not too into.
Yeah, and which you are not advocating on this show.
No, not at this time. Yeah, and so what you have is randomized control trials are not infallible, but they're maybe the best go-to solution. But because there are many situations where you can't do randomization, you're then left in this situation where you can either say, I don't know how to make causal claims in this situation because of all these confounding variables. Or you can say, well, maybe there are clever things that I can do in order to try to make causal claims. And very often, we're dealing with real world, messy data, many potential confounding variables. So many of these approaches rely upon making certain assumptions. And sometimes those assumptions are realistic and you can convince yourself and others that that's the case. Other times, not so much. And maybe you can't always make causal claims. But the real reason why quasi-experiments are cool to know about is because very often in like real world scientific or industry applications, you will be in this situation where you didn't do any randomization and you can't do any randomization in the future. And so do you just throw your hands up in the air, or do you start learning about quasi-experiments and explore CausalPy?
I see. Yeah. And so I think that's pretty clear. So basically, any of those cases, folks, if that's something you are doing, definitely check out CausalPy, because, that should help you at least jumpstart your analysis, because basically, as Ben was saying, it's kind of a toolbox of how to do these kind of experiments in PyMC, in the Bayesian framework. And actually, also, if you want, I think there is also some scikit-learn models, right, Ben? But mainly
that's
out
right.
of the box, by default, it's going to be a Bayesian solution, but you can do some comparison with some scikit-learn models if you want.
Yeah, we've used a Trojan horse kind of tactic, very similar to how the software JASP implements both like traditional OLS frequentist methods, but then also Bayesian stuff. So someone would be able to come along to CausalPy, not really knowing much about Bayes, and just run regular OLS type of approaches. But then if they wanted to, it would not be very much of a leap at all in order for them to basically just do the same analysis, but from a Bayesian perspective.
Yeah, I like that. And I'm switching to Spanish now. So, yeah, okay. So I think that's a good wrap up of CausalPy. And I have so many questions for you at Causal Inference, but we're going to stop there, because I also want to talk about PyMC marketing and maybe teaching. So, PyMC marketing, that's another open source package to which you've contributed. So can you talk to us about that? And mainly, what's the difference between PyMC marketing and CausalPy?
Yeah, so I should definitely express the appropriate humility. So I have largely just been involved in the kind of peripheral aspects of PyMC marketing, working on the docs and some of the kind of promotional activity that we've done. So we've had a whole bunch of people, both inside PyMC Labs and outside as well, who've put a lot of time and effort into that. So I just want to make sure that that's clear to everybody. But PyMC marketing has a similar kind of ambition of making kind of quite complex and sophisticated analyses more openly available to regular data scientists. So this kind of evolved really out of work that PyMC Labs has done with a number of different companies now. So one of the great case studies that we've had was to work on media mix marketing, which maybe we'll talk about, with HelloFresh. And we made some great improvements to an already great model that they had on that front. But in the meantime, since then, we've basically worked with many different companies, all interested in kind of marketing related questions. And what we felt was we would like to package these things up and make them kind of accessible. So the idea there is to just push the envelope a little bit and see what happens. So I'd say it has two core pillars at the moment. The first one would be this media mix modeling component, and that's all about how effective is my advertising. The other pillar would be customer lifetime value, and that tries to address questions like, on a customer level, how valuable do I expect each of these people to be in terms of like ongoing revenue? Because then you can start making decisions like how much marketing money should you put in to begin with in order to acquire a customer? Because if your customers are very expensive to gain through marketing efforts, but you know that they have very low lifetime value, then that's not a winning business proposition. So these two pillars, I think, are quite complementary. So that's my quick overview of PyMC marketing.
Yeah, I like it. So same for people interested, we will put all the links in the show notes. But basically, that's the quick overview. And of course, these two packages are open source, so you can download them for free, use them completely for free. If you find bugs or have feature requests, please open issues, and even better, pull requests. Maybe, yeah, you've mentioned it a bit, MMMs, Ben, but do you have some examples of what people can do with PyMC marketing?
Yeah, so the basic idea of a media mix model is to ask the question of, are my advertising dollars being spent wisely? So the kind of data set that you might be working with is a bunch of time series of how much money did we spend on marketing through social media? How much money did we spend over time through linear TV advertising? And you may have many different advertising channels, and there are lots now with different types of social media channels, for example. Now, if your advertising budgets can be very, very large, like multiple millions, tens, if not hundreds of millions of dollars, and so you don't really want to be just having a guess of how much money you should allocate to each of these advertising channels. So in the past, it used to be relatively easy to work out how effective are different advertising channels because of things like user tracking and cookies and so on. But with the kind of increased concern over privacy, much of that information is going away. And so now the only real information you have is how much did I spend, but then how many new customers did I acquire over time, or how many products did I sell over time. And so media mix modeling essentially is fancy multiple linear regression, which tries to say how many customers or how many sales are being driven by each channel. So that's at its basics, it's multiple linear regression. And then there are some fancy extensions that you can put on top of that in order to deal with more complicated aspects of how you think advertising works, how to deal with multiple different geographical regions or different categories of products, for example.
Yeah, and that's something we've already talked a bit about already on the podcast. Luciano Paz was here to go through the different steps that we took for the HealthFresh model using MMMs. Also, Ellie McDonald Fit was here, so I'm gonna link to these two episodes in the show notes for sure. If people want to dig a bit deeper on how to use media mix marketing models. But definitely super helpful, and the cool thing of PyMC marketing is that it has those models already under the hood, so you can already do an efficient first pass at least on this kind of analysis. We're getting to the end of the show, so I'm actually wondering if, like, looking ahead, what future directions do you see for CausalPy and PyMC Marketing and their integration in industry?
Yeah, so I mean, there's so much you could say about future directions of CausalPy. So we definitely don't want to create an unwieldy beast that just tries to have a go at lots of different types of causal inference. So we do want to retain some focus. But yeah, we want to expand these methods out to hopefully make it quite easy for people to create their own kind of custom models. So we basically provide all the hard work in terms of causal inference, and then people can come along and create their own custom models. What I would really like to see is we're starting to see engagement by kind of individuals, data scientists, and companies now. And so one of the things that I'm really excited about is to basically get engagement with those people and to learn how they are actually using CausalPy, and then let that be a little bit demand driven. But we're an open source project, of course, so we already have a work in progress pull request which will add meta learning capabilities. So that's another causal inference method which is a little bit distinct from what we've got so far. In terms of the integration, sorry.
No, yeah, and maybe are you ready to talk about the do calculus operators that is under development for PyMC, because it's related to CausalPy?
Yeah, so the do operator basically relates back to this idea of making an intervention that I mentioned before. And this is quite a important component when you're trying to analyze the causal effect of a certain intervention. And you can do this in PyMC right now, but it does involve a slight kind of workaround in order to make it work. So if people are interested in how you can do that, then we've got you can look at the CausalPy code now, and there are also a number of really clear examples on the PyMC examples repository that you can get through the PyMC website that show how to do it. But very soon, hopefully a matter of weeks, we will get an official pm.do operator. And this is going to be really cool because what you can do is basically create a causal model, like a regular PyMC model that you think describes your data generating process. You can then provide the model into pm.do, and it will basically do graph surgery, because PyMC has the concept of a symbolic graph, and it will allow you to go into particular variables and intervene and set them to particular values. For example, is someone in a treatment condition or a control condition? And it will basically give you back out a mutilated graph, which is the result of the do operation. And then you can use that in order to basically make your interventional and counterfactual predictions. So that will be really cool when that comes out.
Yeah, that's so cool. I mean, can't wait to have that, and really love to see all of these coming together, right, for the PyMC environment. Basically, that's pretty amazing. That's really awesome. So yeah, thank you to all of you working on that. Of course, we'll definitely talk about that on the show, whether it is a classic episode or even, I think would be even better, would be a webinar format. This format I just started, where the guests come on the show and share their screen and go through a model. I think to demonstrate the do operator, that would be the best thing. So once it's in the package, then you should probably come back to the show in a webinar and walk us through one or two models, and people will ask you live questions. You'll share your screen, and I think that would be the best format to introduce people to that operator and the kind of thinking and the kind of features that now will be available in PyMC. So yeah, and FYI people, so those webinars are open to everybody, but you get at least a 50% discount on these webinars if you are a patron. A lot of you can just access them for free, and you get access to the recording 1 month before everybody. So subscribe, support the show on Patreon. That helps a lot, actually, for the editing, for a lot of stuff. And actually now we're recording the show on Riverside, and so that makes everything easier, especially for the guests. So I have to pay for Riverside. It is not cheap, but I find it makes the experience way better for everybody. So thank you to all of you who are contributing every month, even if it's a small amount. I am eternally grateful. That helps not only for editing, but for making the whole show better. So again, thanks a lot to everybody. And oh yeah, Ben, I wanted to ask you about education a bit before closing up the show, because we often teach workshops together, which is always a lot of fun. And you've actually taught very recently the first causal inference module that you developed very recently at the time of recording this podcast. And I'm curious, what would you say are the key skills to develop to start learning Bayesian stats?
So, if I were to go back in time and give myself advice, number one would be don't just buy the book and let it sit on your bookshelf. You actually have to dedicate time to engage with it. But for all of you with more willpower than I have, I think one of the key things that works for me is to kind of really engage with whatever book and educational material you have. And what I mean by that is don't just kind of passively read, but actually code along, experiment, work through the examples that you're given, because that turns it very much into play. And just in the same way that how it was when I was learning BBC Basic back when I was very young, by experimenting and playing around, it allows you to see where you have gone wrong, where you understand correctly, and where you have misunderstood things.
Yeah, for sure. That's I would second that and say that's definitely a very important skill to develop. And something like, have you noticed any, common biggest difficulty Bayesian beginners face usually when you teach Bayesian stats, or more generally, what do you think the biggest obstacles in the Bayesian workflow are currently?
So, this might sound provocative, but it's not meant to be. I think one of the biggest challenges is the fact that people have been exposed to frequentist ideas for so long. Mm-hmm. That's not to say that they're wrong, but they do shape your thinking. And so there can be quite an intellectual twist that happens when you get exposed to Bayesian ideas. So I think that just running simulations, simulating data, just using whatever programming language you have, is probably a good way to kind of start making that conceptual twist in your mind. Because once you see that, oh, I can create a data generating process by using random numbers and having some variables depend on other ones, I think that really helps understand the Bayesian concepts. But in the past, I would have said that the rate limiting factor would have been availability of decent intro level books and the packages, but that is definitely not the case anymore. So there are tons of kind of really good intro to intermediate level Bayesian resources out there. And just to kind of interpret your question a little bit more, I'd say that we're maybe just at the beginning of a similar transition with causality. So I think that there's lots of potential for packages, maybe like CausalPy, but also educational material to make it much easier for practitioners to get a grip on things.
Yeah, that's true. I had not seen it like that, but that's a good point about where we are with causal inference also. For sure, that's something very interesting and something I will be very curious also when we teach this material more frequently in the workshops, because that's definitely a topic that's very much on top of people's mind. This idea of interpretable models and white box models. This seems to be very important for people, which I understand. I definitely share that concern. So yeah, cool. Maybe before asking you the last two questions, looking ahead again, I'm wondering if you have if there are some areas that you are most excited about for patient stats in the future, and what would you like to see and what you would like to not see?
I think kind of two things that I'm excited about, and this is not to say that I have any specialist knowledge or expertise in these areas, but one thing that I'm really interested in is what it becomes possible in a probabilistic programming language when you have a language like Julia. So what I mean by that is in order for packages to do Bayesian inference, we need gradient information. And at the risk of just diving in a bit, in PyMC, we calculate gradient information by having a graph which allows you to do auto differentiation to calculate the gradients, and that's cool. But it does kind of mean if you want to do anything exotic, you have to learn a library that allows you to do that. So right now, the one that we're relying on is PyTensor. Now, in Julia, you still have to find gradient information if you want to do efficient Bayesian inference. But now, the thing that is slightly different is that there are packages in Julia which allow you to do auto differentiation on base Julia code. And what that means is for the user, they don't then have to learn a kind of a custom package that does auto differentiation like PyTensor. They could just learn base Julia, write some kind of like reasonably arbitrary model, and then just run inference on it. So that to me is kind of really exciting in terms of making relatively complicated models accessible quite easily. The other thing I'm interested in, and I think that PyMC is kind of making great progress here, is doing operations on the graphs. So
Yeah.
all PPLs basically give you a log probability and hopefully gradient information, but not all of them have kind of like an underlying explicit graph structure. But when you do have that graph structure there, then what that means is you are able to go in and do surgery on the graphs. We've talked about one clear example of that with the do operator, where you can go in and replace a random variable with a constant, basically, and cut nodes into this thing that you're intervening on. But other applications of this would be graph simplification. So in the case where you have conjugate priors, for example, you could presumably write some code to find situations where you can go in and massively simplify the graph, and so minimize the amount of computation time that you have to do. So I don't do any of this stuff. I don't implement any of it, but those are two things that I'm excited about at the moment.
Yep, I understand. that does sound super cool. Yeah, I love it. And that it's true that limitation of where you have to learn another package all the time can definitely be a limitation. And that's also why, to basically have a loop of the whole show, developing that ability and that skill to fail comfortably and quickly is really important, because then you are more comfortable learning things that make you very uncomfortable at the beginning. Any other topic that I didn't ask you about and that you'd like to mention?
No, I think we've done a really good job at covering quite a lot of different things.
Yeah, I think that was quite a lot. Thanks a lot for that comprehensive overview, Ben. So, before letting you go, let me ask you the last two questions. I ask every guest. It's better at the end of the show. So, first one: if you had unlimited time and resources, which problem would you try to solve?
So I think it depends. Am I the only one who has unlimited time and resources, or do other people?
Let's say that's just you.
Okay, so that puts quite a lot of pressure on me, because that would suggest that I focus on the problems that will benefit the most people. So if that was true, I guess I'd have to kind of say something like creating a circular, sustainable economy. Because as someone, I don't know who, likes to say, anything that's unsustainable will not be sustained. So zooming out, taking a kind of a sci-fi view, or a long-term view of human history, we clearly need to live within the kind of energy and material boundaries of the planet. Otherwise, things don't look so great.
That is, unfortunately, I would say, a common answer to that question. The cool thing is that a lot of people answer that, so you folks can all have unlimited time and resources to work on that. Second question: if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
So, I think maybe because I don't have like a formal statistical training, I didn't feel like I had a great wealth of knowledge to really pluck someone out of the air. So I'm going to be slightly controversial in that I don't know if you could classify them as a scientist, but maybe the Buddha. I think that would be interesting. You could claim that, you know, the they were empirical because they're paying attention to what happens within one's mind, for example. And you could argue that they were experimental because they tried different approaches to life and meditation, and kind of saw that some of those things didn't work and then moved on to a different approach. So I don't know if anyone's going to buy the fact that the Buddha might be a scientist. I'm not really sure, but I'm not really sure how much they would speak either, to be honest. But I think it would be an interesting thing to write a blog post about.
Yeah, probably they would ask you a lot of questions. So probably be that. But definitely an interesting conversation. Yeah, I like that answer. I would not say that qualifies as a scientific mind, but I do like the thought that you give to the question. That's definitely interesting, and that would make for a very interesting dinner for sure. So yeah, thanks for that answer, Ben. You're definitely the first one to answer that.
Great.
Okay, awesome. Well, I think that's it. Let's call this a show. Thanks a lot, Ben. I learned a lot, honestly. I'm really happy that we managed to do that episode. So many things. As we said, let's do a webinar once the do operator is out in PyMC, and we'll walk you folks through the webinar so that you can readily use that afterward in your own modeling. And other than that, as usual, I will put resources and a link to your website in the show notes for those who want to dig deeper and connect with you. Thank you again, Ben, for taking the time and being on this show.
Yeah, thank you very much for having me. It's fun.
Let me show you how to be a good Bayesian. Change your predictions after